Okay, we're ready to begin Chapter 2, which is on power, polynomial, and rational functions. In Lesson 2.1, we have two clear objectives, and one is to graph and analyze power functions. And in the second objective, we are to graph and analyze radical functions and solve radical functions. So we'll attack that first objective today and take a look at the power functions, some of which we are very familiar with, and others we may need to refresh a little bit. So our first objective, like I said, is to analyze power functions. So first of all, what is a power function? We're very familiar with these, but we're going to highlight a couple things. A power function is any function that can be put in the form f of x equals a to the n. And we'll see some very familiar functions that we've looked at before. A power function is also called a monomial function just because it's only going to have one term. And typically, just to show you an example very quickly, f of x equals ax squared plus bx is no longer a monomial because there's 1, 2. So there's two monomials. So that is called a binomial. So just a quick little glimpse of what do they mean by monomial. Monomial is a single-term polynomial. Our single-term polynomial that we're looking at is any form of f of x equals a times x to the n. So monomial power functions. We're really familiar with them, so let's take a look at a few of these. Basically, we have two shapes. We have U shapes and we have S shapes. The U shapes are going to be any time you have a positive exponent on n. We're going to take a look at some graphs of these. All that A is going to do, like we already learned in the last chapter, A is going to be a vertical stretch or a shrink. So anytime we start changing that A, the bigger A gets, the more that we stretch the graph vertically. When the number or the value of A gets between 0 and 1, we're going to shrink that graph vertically. So that's the value of A. Let's say A is positive. Because it is positive, it'll open up as a smile. So any even power that is positive, and A is positive, is going to be a smiling graph or a U. Over here, they just make a negative, and of course, whenever we put a negative in front, we learned in the last chapter that's going to reflect it across the x-axis. So we have U-shaped graphs in our power models, and we also have S-shaped graphs. And these are when our value of n is odd. So now we're looking at values when n is odd, like x cubed, x to the 5th, x to the 7th. Again, I want to go into more depth of what those graphs look like in a little bit. But if it's positive, if A is positive, it's going to go from low and finish high. We've had this before. And if A is negative, then it starts high and finishes low. So it's high to low on a negative graph. Very familiar with those. We're going to quick jump to a different program here, and I want to just take a look at what happens to these and give you a general description of these graphs. We're going to graph a series of power models. One is going to be x squared, and the other one is x to the 4th and x to the 6th. Just want to let you see the general nature of these graphs. The first graph I have drawn here is our basic y equals x squared. So this graph is our most basic power model with an even power. Now, what happens when we raise it to the 4th power? So I'm going to go and quick show you a graph of it. And you can see there's a change in this graph and get a little better color there. When we go to y equals x to the 4th, notice it's still an even power, so it's still going to be a U-shaped graph. But as you raise numbers to larger powers, anything bigger than 1 out here, as you raise these numbers to larger and larger powers, the rate of change is going to be greater. So as we take, the good point to always observe is 1. When you take 1 and you raise it to the 2nd power, it's not going to be any different than you take 1 and raise it to the 4th power. So as you notice in all these graphs that I'm going to show you, whether it's 1 or negative 1, they're going to be exactly the same value. Anything outside of that range, so I'm talking about numbers that are larger than 1 or smaller than negative 1, your graph gets rather steep. So it's steeper on the outside than our parent function graph. So as this power gets larger and larger, you're going to see on the outside of the negative 1 and a positive 1, the graph gets steeper. But more strangely, maybe, it really doesn't make sense, inside of here, inside of negative 1 and 1, as you raise fractions, because these numbers are fractional numbers such as a half. If I raise a half to the second power, it's just a fourth. But if I raise a half to the fourth power, then we get 1/16. So then it becomes flatter. So the general description I make on these, as the power gets bigger, go from a 2 to a 4 to a 6, and I'll show you 6 in a moment. It'll get flatter on the inside between -1 and 1, but on the outside it will get steeper. So I'm going to clear that ink off of there for a second, and then we'll graph on the same coordinate, y to the 6th. Okay, it's still an even power. It will be U-shaped. The only difference is this U-shape will be flatter on the inside between -1 and 1, and steeper on the outside of -1 and 1. And again, they still have the same point in common. It's a good point to track whenever you're using some of these graphs. So those are our U-shapes. They're power models. They are power models raised to an even power. I'm not going to go through and put negative values of A in there. All they're going to do is reflect it across the x-axis. So then the next group of, or family that I want to look at here is a power model with odd powers. So x to the third, x to the fifth, x to the seventh. Here's our basic family of our cubic function model. So this graph is y equals x to the third. So what kind of behavior can you expect to find when you have y equals x to the fifth? Is it going to follow the same map model that we saw before? So we're going to graph y equals x to the fifth and let you take a look at what happens to the graph. Notice, is it going to get wider inside of -1 and 1 and steeper on the outside as the others, or is it going to behave differently? So here is our graph of y equals x to the fifth. I'm hoping that you're observing that the same features are basically happening in here. So in between a -1 and 1, that was our black graph. I'm just going to highlight it in green. It got a little bit flatter in between -1 and 1, and on the outside it got steeper. Again, the same nature. The numbers that we're putting in here inside of -1 to 1 are fractional numbers, and just for convenience I like to use a half. We take a half and raise it to the third, that is 1/8. You compare that to a half raised to the fifth, and 2 raised to the fifth, I believe, is 1/32. So for the same input value, we've got to get a smaller output value, and it's getting flatter. You take that on the contrary side, when you go on the outside, numbers bigger than 1 or smaller than -1, then we're going to start seeing a rapid rate of change. So anything bigger than 1, we're going to have a rapid rate of change, and it's going to be steeper than our parent graph of y equals x to the third. And anything smaller on the inside is going to have a slower rate of change. We're going to clear this ink, and we'll take a look quickly at the third one as a model example. What happens when we go x to the seventh? Again, what we should notice is it's going to get flatter on the inside between -1 and 1, and wider the outside in the red graph. Our maroon graph is modeling that. So here, these are the power models they introduced in this unit, starting right away with even and odd powers. And those are the nature of our graphs. Keep in mind, there's really only two different shapes. It's a U or an S. We can reflect about the x-axis, and that way we'll have either increasing graphs or decreasing graphs. So with that in mind, they ask us several questions about these graphs. Here's an example of, well, two examples of what they would like us to be able to do. They want us to graph and analyze each function, describe the domain of range, intercepts, end behavior, continuity, and where the function is increasing or decreasing. So we've got a lot of things to do in here, but they go pretty quickly. And I'll try to make room on this page so we can see everything. Otherwise, I'll probably have to erase, and hopefully through the video you can pick information up. So first thing, just try to think through this a little bit. If I took out this 3, what would an x to the 6th graph look like? Well, x to the 6th graph has to be the U shape. It's going to be wide on the inside, as you see. It's a little bit wider looking than our normal parabola, and that's a little bit steeper on the outside. But the order pair 1, 1 and -1, 1 is still intact. So what I did is I graphed that. I just graphed y equals x to the 6th. And then I want to just kind of review a little bit about what we did in the last unit. What does that 3 out in front of it do? Well, since it's on the outside of the grouping symbol, this is a vertical stretch of 3 units. So we want to multiply all of our outputs by a factor of 3. And as I mentioned, I want to keep track of this order pair 1, 1. because in our new graph, when it says y equals 3x to the 6th, all of our outputs from our original graph should be tripled. So the order pair 1, 1 is now going to become 1, 3. The order pair negative 1, 1 is going to be 1, negative 1, 3. So we have this vertical stretching. So with that in mind, I want to review that. Let's describe the domain. If we look at our graph, our domain looks as though we could open it up to all real numbers. There's several ways we can write the domain. I'll write it this time using our interval notation. There are no gaps, there are no breaks. What you're looking for on these domains when you look at your graph, look for holes, look for places where you see a vertical asymptote, jump discontinuity. But if you look at this as a nice, smooth, continuous curve, it never has any gaps or any breaks in it. So our domain goes from negative infinity to infinity. Next thing they asked us, I believe, was the range. On a range, now I want to look at the outputs. Where do these outputs go? Is there a lowest limit for the outputs? Well, there is a lowest limit. The lowest point that this graph achieves is down here at the origin. So the lowest point is at 0, because if you put in 0, 0 to the 6th power is 0, times 3 is 0, and then it goes up towards positive infinity on both of them. So the y values, or your ranges, go from 0 to positive infinity. All right, the next thing they want us to discuss was the intercepts. That's a fairly easy question to answer. The intercept is at the order pair 0, 0, so both the x and the y intercept can be placed at the origin or the order pair 0, 0. Next thing they ask is end behavior. For end behavior, what we want to do is analyze, as x approaches a positive infinity, where are the y values going? Well, as x approaches a positive infinity, as x gets large, the y's go to positive infinity. As x approaches a negative infinity, then what happens with the y values? So now we want to trace the x's so that they go to negative infinity. As x's go to negative infinity, the y's are still going upward towards positive infinity. So now we've just described the end behavior. Next thing, continuity. We've already talked about this as I've gone through the problem. There are no jumps, there are no gaps. This thing is continuous throughout the entire domain. So if you want to talk about the continuity, it is continuous from a negative infinity to infinity. And where is this function increasing or decreasing? When you answer this question, what you want to make sure that you're thinking about is reading the graph from left to right, just like you're reading a book. So as you read this graph from left to right, this is falling from left to right until we get to the origin. Right here at the origin, there's a transition. So from, and we're going to describe this as decreasing, as we go from negative infinity to 0. We're not going to call 0 part of this decreasing point because that's where the transition is taking place. It's going to be increasing, though, from 0 to positive infinity. Very good, positive. So we just described the characteristics that they wanted us to describe on this graph. Here's your, from left to right, our graph is increasing going upward. And that was our first guided practice. So we'll try the next one, 1B. Same directions. What I did is I graphed the parent function. To me, the parent function on this one is where y is equal to x to the 5th. That's the graph I have here in red. Again, it's an S shape. It's going from low to high because it's a positive x to the 5th. It's a little bit wider than our cubic graph that we've been dealing with lately, but on the outside it's a little bit steeper. But the order pair 1, 1 is still here, and this one, a negative 1 is here, because when you put in a negative 1 raised to the 5th power, you get back to negative 1. So we're going to use those to help us track kind of the transition and change in this graph. So what are the things that they've done to our parent graph? First of all, I'm looking at this negative sign, and the negative sign is going to flip our graph about the x-axis. So this part here is going to get flipped about the x-axis, so it rotates down here. And this other part that was below the graph now it gets flipped about the x-axis or reflects across the x-axis and goes upward. So that's why we have the high to low shape. All we did is we reflected about the x-axis. The other thing that has happened on this graph is that we have multiplied by 2/3. This is a vertical stretch or shrink. So we've got to think about, did it stretch it or did it shrink it? Well, verticals are pretty intuitive. If this number is between 0 and 1, it's going to be a vertical compression, or it's going to shrink. It's going to compress it and shrink it down towards the x-axis. So what we normally get in our graph is the order pair 1, 1. So now when we do this and we compress it 2/3, and it's a little hard to tell because of the scale, but this is about as good as I can get it. You can tell it is not as high as it used to be. It's not at 1 anymore. And I'm just trying to get you to recognize is that point is at 2/3. So now the order pair 1, 2/3 is on the graph, which did compress it towards the x-axis, or was a shrink. Okay, now let's get to the business of what they asked us to do. What is the domain of this function? Again, on the domain, whenever I'm thinking of a domain, I'm looking across the x-axis and I'm looking for any breaks or gaps in this graph. This is a nice, smooth, continuous curve without any gaps or breaks in it. About the only types of graphs that we're going to see some breaks in would be if we divide by 0, or if you have removable discontinuity that we've seen. Another possibility could be the square root of negatives. That's where we're going to have some domain limitations. So this thing has a domain from -infinity to infinity. We're just saying all real numbers. The range. Now in the range, we're trying to describe the y values. So when I start describing y values, I'm looking both up and down. How far up and down does this graph go? And even though they don't have arrows on it, we know it's going from -infinity all the way to infinity, because our graph continues below and above that. Next thing, the intercepts. So again, if we plug in 0 for x, we're going to get back a 0 for y. So our x and y intercept are again, as it was last time, at the origin. So they're going to be at the order pair 0, 0. End behavior. Every time we entertain the question of end behavior, what we want to make sure that we do is we answer the question, what happens as x approaches a positive infinity to the y values? What does y approach? Well, as x approaches a positive infinity, now the y's are going downward, so y's approach a negative infinity. And the other side of it is, what happens when we let x approach a negative infinity? We're only concerned with the end behavior of the graph, so as x gets really large, the y's are climbing, so that means the y's are going towards positive infinity. So that's our end behavior. Continuity. There are no breaks, there are no gaps. So no jump discontinuity. This graph is continuous over the entire set, so all real numbers. So for continuity, it's going to be from -infinity to infinity. And finally, where is this graph increasing or where is it decreasing? Remember, we want to read the graph from left to right. What's happening as we move along the x-axis to our graph? Well, our graph is coming downward, stays downward. It flattens a bit, but it's still coming downward. So in this graph, it's decreasing everywhere and it's increasing nowhere. So what we're going to put on this is decreasing from a -infinity, not an 8, -infinity to positive infinity. Where is it increasing? Nowhere. So we can put nowhere, or there'd be an empty set. So that's the discussion for questions 1A and 1B. I'm going to break it at this point so I can transition to the next slide.